welcome back. So this is lecture 15 in this course on Bayesian modeling. So the topic of today's lecture is Bayes theorem. Okay, so this is actually the lecture in which I will introduce what exactly is Bayes theorem and how we can use it for statistical inference. So this is a very foundational lecture for this course. Okay? But so far we have been building up to this lecture. So for example, we discussed probability, random variables, some probability distributions, some common examples of probability distributions. Then we discussed the likelihood function, and then we discussed some concepts like conditional probability and total probability, so that we can understand what exactly is Bayes theorem all about and how do we use it for statistical inference. Okay, so just to revisit a couple of concepts that we covered in the previous lecture, we discussed conditional probability. Okay, so we discussed concept called conditional probability. So let's say you have two events A and B, okay, which belong to your event space F. Then probability of occurrence of event A given that event B has already occurred. So this is called conditional probability of A given B. Okay, so we discussed a formula for this. The formula is probability of A intersection B, so probability of joint occurrence of A and B divided by probability of B, such that probability of B is not equal to 0. So that's a formula of conditional probability of event A given B. Okay, so this is one thing that we discussed. We also discussed independence of events. So independence of events implies that probability of A given B is equals to probability of A, which eventually applies that if two events A and B are independent, right? A and B are independent if probability of A intersection B is equals to probability of A into probability of B. You can say vice versa as well. If A and B are independent, then this should hold, right? Third thing we see was the law of total probability. So you can actually calculate total probability of any event B. Let's say B belongs to an event space F, but there are some events, let's say A1, A2, A3, such that they are mutually exclusive, so they do not contain any common element. They are mutually exclusive as well as they are exhaustive. So their union is actually your sample space, right? So these are called mutually exclusive and exhaustive event. Okay, so if this is the case, then total probability of event B can be given by summation of probability of B given AI into probability of AI, right? So AI basically can be A1, A2, A3, A4, so on, right? So basically summation across probability of B given AI into probability of AI, right? So if we do this summation, we will get total probability of B. So this is the law of total probability. Okay, so these concepts will become useful for understanding the Bayes theorem. Okay, so let's say you have two mutually exclusive and exhaustive events, A1 and A2. Okay, this is your sample space omega, such that A1 intersection A2 is an empty set, so they are mutually exclusive, and A1 union A2 is your sample space omega, so they are exhaustive events. And let's say there is a third event B, so this event is B. Okay, now if I ask you what would be the conditional probability of A1 given B, conditional probability of event A1 given that event B has already occurred, okay, what it would be? Well, it would be probability of A1 intersection B, right? A1 intersection B divided by probability of B. Okay, so I just applied the formula of conditional probability here. Similarly, if I ask you what would be the probability of B given A1, okay, so now it is conditional probability of B given that event A1 has already occurred. So according to formula of conditional probability, this should be B intersection A1 divided by probability of A1. Okay, so I just applied the same formula of conditional probability here. But notice the numerator in these right hand side terms here, this and this. So here you have probability of B intersection A1 and here you have probability of A1 intersection B. Are these two events different? B intersection A1 and A1 intersection B. Well, they should be same event. You are just writing them in different order. So B intersection A1 will be the same event as A1 intersection B. We are talking about the same event. So that means the probability of B intersection A1 and probability of A1 intersection B should be the same. Okay. So the numerator in right hand side terms should be equal. What does that imply? So let's say this is equation 1, this is equation 2. What it would imply from equation 1 and 2 is this, that probability of B given A1 into probability of A1 is equals to probability of A1 given B into probability of B. Okay, so this is the result we are getting. Now you can actually rewrite it to get probability of A1 given B. Okay, so probability of A1 given B can be written as probability of B. So I'm just rewriting this equation. B given A1 into probability of A1 divided by probability of B. Okay, so this is what I'm getting so far. Well, from law of total probability, can you figure out what would be probability of B? Yes, because these events A1 and A2 are mutually exclusive and exhaustive. So you can write probability of B should be equal to probability of B given A1 into probability of A1 plus probability of B given A2, basically summation across all such terms, probability of A2. Right now we have just A1, A2, so you can just write it like this. So that is total probability of B. So now you can replace probability of B in this formula with this. So the final formula you will get for conditional probability of A1 given B will be probability of B given A1 into probability of A1 divided by probability of B given A2, A1 into probability of A1 plus probability of B given A2 into probability of A2. This theorem or this result is called the Bayes theorem. Okay, what it says that probability of an event A1 given B is given by probability of B given A1 into probability of A1 divided by adding this same term across all mutually exclusive and exhaustive events. Remember the same numerator term, so probability of B given A1 into probability of A1. The same term is repeated in the denominator, but for each mutually exclusive and exhaustive events. So if you have 6 mutually exclusive exhaustive events, it would repeat basically 6 times A1, A2, A3, A4, A5, A6 like that. Right? So that's your Bayes theorem. Okay, so probability of any event A1 given B is equals to probability of B given A1 into probability of A1 divided by total probability of B. So basically across all mutually exclusive and exhaustive events from A1 to AN. Okay, this is the Bayes theorem. Now how do we use it for statistical inference? Okay, that's what we want to see. Right? So let us take an abstract example. So let's say you have the outcome of a random event or an experiment is basically values of this random variable x. So basically, let's say you obtain xi, or let's say you obtain the outcome x from any experiment, right? So basically, it's a value of your random variable. So let's say this is the outcome of the experiment x, right? And you assume that the outcome of this experiment, let's say, comes from, let's say, probability density function f of x theta. Okay, so this is the probability density functions which assigns probabilities to events in this event space, right? So this is your assumption. You have assumed that outcome of this experiment comes from this probability density function. Okay, now let's say there is a space. Okay, we can call it the parameter space. Okay, what it means is that basically all the values that parameter can take. So what is the parameter here? Theta. So let's say hypothetically, of course theta would be continuous in most cases, but let's say hypothetically theta can take 5 possible values. Okay, so let's say theta 1, theta 2, theta 3, theta 4 and theta 5. Okay, so we're assuming that theta can take 5 possible values. Okay, so these would be basically then mutually exclusive and exhaustive events, right? So if you think about each theta value as an elementary event, then these would be mutually exclusive and exhaustive because they do not have any common element. These are all 5 distinct discrete point values, right? So these will be mutually exclusive and exhaustive. So your parameter space has been divided into 5 discrete points. Okay, now let's say you have collected some data and your data is, let's say, x obs. Let's say this is your data. So you collected data from this experiment. Until this point we just had this assumption, but now let's say you collected the data and your data is x obs. So it could be any number, let's say. Okay, now what would give me probability density of observing this data given this probability density function? Okay, how do I calculate probability density of observing this data given that I'm assuming x obs comes from f of x theta, right? So it can be given by, so basically you can write it like this: probability density of observing exactly this data x obs given a particular value of theta. So let's say theta 1. So this thing would give me probability density of observing x obs given a particular value of theta, right? But what I'm essentially interested in is in knowing that what is the probability density of a particular value of theta that it has generated given this data x obs, right? So given this data x obs, what is the likely value of theta, or what is the probability density of a particular value of theta? So this is precisely the thing I want to calculate, because this is more informative for me, because I want to know the distribution of theta. Okay, I want to know what value of theta has what probability density. Okay, so can I calculate this conditional probability of any value of theta? Let's say theta 1, I can calculate the same for theta 2, theta 3 and so on. So conditional probability of theta 1 given this data x obs. Why I'm interested in probability density of theta 1, theta 2 and all these, basically the probability distribution of theta? This is because in Bayesian inference we are treating that theta is a random variable. I will come back to this point later, but right now if you are having this question in your mind that why we are interested in the probability distribution and not just point value, this is because theta, we are treating theta as a random variable. Okay, so theta is not a constant point value. Okay, anyway, So we are interested in calculating probability density of each value of theta. So for theta 1, theta 2, theta 3, theta 4, theta 5 given this data. Okay, because this data is known. So after you have observed the data, this quantity is known. So basically you can think of it like this, that this event has already occurred. So basically data has already been observed. Okay, so after observing the data, what is the probability density of each value of theta? Okay, so that's what we want to calculate. How do we do this? So if we apply Bayes theorem here, okay, so if you apply Bayes theorem, probability density of theta 1 given x obs, right? So the Bayes theorem would say that this should be equal to probability density of x obs given theta 1 into probability of theta, right? I'm just applying Bayes theorem. See here, probability of A1 given B is equals to probability of B given A1 into probability of A1 divided by total probability of B. And total probability of B means that you are summing the same numerator term across all mutually exclusive and exhaustive events. Okay. So in this case, the numerator is this, probability of x obs given theta 1 into probability of theta 1. Now the denominator would be probability of x obs given theta 1 into prior probability of theta 1 plus probability of x obs given theta 2 into prior probability of theta 2 and so on. Now you will sum it across all these 5 possible values of theta, right? That's what will go in the denominator. So this is how you can apply Bayes theorem for inference. How we can use it for inference? What exactly we are inferring here? What we are inferring here is that you have this term is actually your likelihood function. Okay, so the first term in the numerator, Px obs given theta 1 is likelihood of theta 1 to generate the data x obs. That how likely is theta 1, this parameter value theta 1, to generate the data x observed. Okay, so this term is the likelihood. So likelihood of theta 1. Okay, the second term, probability of theta 1, this is called prior probability density or prior probability of theta 1. Okay, what does this mean? So you notice that this term does not have any x obs component. This term does not have any data term, right? So there is no data in this term. So this is the prior probability of this parameter value theta 1 before seeing any data. So this is probability density of theta 1 before seeing any data. So how likely it is that the true value of this parameter is theta 1, okay, before seeing any data. Okay, we will come back to later what does it mean theoretically and how we apply it in practice. Okay, but for now it's the probability density of theta 1 before seeing any data, right? This might change after seeing the data. So this prior probability might change after seeing the data, but right now this is called the prior probability, right? The term in the denominator, right, it's basically total probability of observed data, right? So you are summing probability of x obs given theta I into prior probability of theta I from I is equals to 1 to n. This is called total probability of x obs. There is another name for this, which is marginal likelihood. So you also call it the marginal likelihood. Okay. Okay, so this is the denominator term. that basically this is the total probability of your observed data. So what is the total probability density or total likelihood? You can interpret marginal likelihood like this. What is the total likelihood of observing this data across all possible parameter values, right? So let's say this data cannot be generated by theta 1, but it can still be generated by theta 2 and theta 3, and let's say it cannot be generated by theta 4 and theta 5, right? So although theta 1 does not contribute to generating this data, theta 4, theta 5 also does not contribute to generating this data, but theta 2 and theta 4 does to a large extent. We are trying to figure out what is the total likelihood that this data was generated by this model by summing across all possible parameter values, right? So it would have some likelihood to be generated by this, some likelihood to be generated by this. So we are summing that all up, right, to get marginal likelihood that the model has generated this data x obs, right? So these are the terms on the right hand side. On the left hand side, what you get as a result, so this is conditional probability of theta 1 given the data. This is actually called posterior probability density, or you can simply call it posterior density of theta 1 given the data. Okay. So see what is happening here. There is a term which is called prior density of theta 1. So before seeing any data, okay, what is the probability density of that the true value of the parameter is theta 1. Then you see some data, and after seeing the data you can calculate what is the likelihood that theta 1 would generate the observed data, and then you are multiplying this likelihood and the prior density to get this posterior density. Okay, and posterior density is actually the probability density that the true value of the parameter is theta 1 given the data x obs, okay, and given your prior assumption about the parameter which is p of theta 1. So given the data and your prior assumption about theta 1, okay, so given this likelihood function and given this prior assumption, okay, what is the probability density of theta 1, right? That's what is the posterior probability. Okay, and why this is important to calculate posterior density? Because this is what gives us the distribution of true value of theta. Okay, so this distribution will tell us that given this data, what values of theta are likely. So basically, what distribution might have generated this observed data given your assumptions and given your prior distribution assumption about theta. Okay, so this gives us what values of theta generated the data considering the data as well as our prior assumptions, right? So this is called posterior distribution of theta. Okay, so because you will get this the same thing. So right now we have calculated this for x obs for theta 1, right? You will also calculate the same thing for theta 2, right? You will also calculate the same thing for theta 3, same thing for theta 4, same thing for theta 5, right? Once you have all these theta 1 p theta 1 x obs, p theta 2 x obs, right, all these posterior densities, you can draw a graph where let's say you have these 5 values of theta on the x axis, theta 1, theta 2, theta 3, theta 4, theta 5, and the densities on y axis. So p theta given x obs, right? So whatever posterior density you get, and let's say the posterior densities are like these. Okay, so this is a distribution now, right? This is a distribution p of theta given x obs. This is a proper probability distribution, and the purpose of this denominator term is exactly to ensure that this term becomes a proper probability distribution, right? What is the condition for being a proper probability distribution? That the area under the curve should be equal to 1, or the summation, if it is discrete, then the summation of all these probabilities should be equal to 1, okay, according to second axiom. So we get this proper probability distribution, right? And what this probability distribution tells you? It tells you the basically probability density of different values of theta given the data and your prior assumptions, right? So how likely that a particular value of theta would generate the data, okay, given the observed data and your prior assumptions p theta, okay. So given the data x obs, likelihood assumption, what is the likelihood assumption we have? So likelihood assumption is the same assumption that you are making about how the outcomes are generated in this experiment. So likelihood assumption is x obs comes from f of x theta, okay, or you can also write it like this: x obs comes from p of x obs given theta. So given this likelihood assumption and prior assumption, what is prior assumption? That theta comes from p of theta, okay. So given these assumptions, okay, what is the probability density that theta 1 or any particular value of theta would generate the data, right? Observed data x obs, right? So given the likelihood assumption and prior assumption, what is the probability density a particular value of theta 1 would generate the data, okay? So we are calculating probability density of a particular value of theta given the data, right? And that basically we have seen that probability density of any particular value of theta of parameter given the data is actually likelihood of a particular value of theta that it would generate the data, prior probability density of theta, prior density of theta divided by marginal likelihood, okay. This is what we have seen, okay. So by the way, what would happen if theta is a continuous space? So right now you assume it's discrete, so you have discrete values of theta. Well, when it would be a continuous space, then rather than summing all these values, right now you're summing x obs given theta 1 into probability of theta 1 plus x obs given theta 2 into probability of theta 2. Rather than summing across these terms, what you would have instead, let's say if theta is continuous, then the denominator, the marginal likelihood will become like this. It will be probability density of likelihood of particular value of theta, prior density of theta, d theta, and you will integrate it through the space of all possible values of theta. So let's say theta can go from minus infinity to plus infinity, so we'll integrate this from minus infinity to plus infinity, okay. So this is how you can apply Bayes theorem to infer what values of theta might have generated the data. So given this data, assuming data is fixed and known here, okay. So once data is known and fixed, then what is the probability density of different values of theta? To know the distribution of theta, okay? We are trying to know the distribution of theta, assuming theta is a random variable, okay. So what is the true distribution of theta? That's a more precise term. We want to know the true distribution of theta given this data, okay, and that would be basically your likelihood term, likelihood of a particular value of theta, prior density of particular value of theta divided by marginal likelihood, okay. That's basically we are using Bayes theorem for statistical inference here, and this is the basis of Bayesian inference. We will go over it once again in the next lecture. We will work out exactly how we would use it, use the Bayes theorem in practice. But this is the basic idea behind using Bayes theorem for inference. Okay. All right. Thank you very much.